So, last lecture on Monday, we started talking about chapter 4 and see how we're going to design a very small scale processor enabling us to do some basic arithmetic functions, some branch functions. And just like we arrived to the point that we were talking about those three specific instructions, such as branch and R format, which was for arithmetic instructions, and then the load and store instructions, right? I'm just going to recap what we discussed there. So these were the first of the three. Is going to implement a branch function, branch BEQ, x1, x2, and go to offset, right? We talked about it in a previous lecture. So first, we need to compute the branch target address, right? By adding the sign extended offset field of the instruction to the PC. And then we talked about this shift left 1, which was simply just a rerouting of the wire of the signal between the input and the output. The output was adding 0 in base 2 to the low order, right? And we also mentioned that no actual shift is happening here because the amount of the shift is constant, right? So we just throw out the sign extended offset instead, right? Because we know that the offset is on the 12 bits, so the shift will just simply throw out only the sign bit, okay, instead of the shift. And we mentioned that the control logic will be used here to decide whether we're going to increment the PC by 4 or we're going to go towards the branch target, which we decided. Okay, so that was one of the three instructions we talked about for the logic design for our data path. Okay, the second one was the R format arithmetic instructions, right? For which we need 2 read register operands, right? So the goal is to perform arithmetic or logic operation. Later on today, we're going to see how we're going to control this using a control unit. Okay, so here we need also a write register. So we call this a register file, which includes the set of registers you have. And also I mentioned that the reason we have 5 here is because in RISC-V we have 32 registers. And the width is either a word or double word, right? So 32 or 64. So using this, it's as if I can have 5 lines. So this is a simplified version of having 5 lines. Each of them are a signal, right? Either 0 or 1. So with this, I have the option to choose either 0 or 1 on the first line, the 0 or 1 on the second line, 0 1, 0 1, or 0 1. So you have 5 2 options, which lead to a 32 option, right? 2 to the raise of 5. And we mentioned that the register file always is going to output the content of the registers corresponding to the read register, right? For the read registers, we don't need a read register wire, just like what we have for the write. Okay, but for the write, because we are trying to write data, we need another controller that sets the write on while we are writing. And just like I mentioned in the previous lecture, because the convention is we are doing the writes also on the edge triggered clock, right? So all the values must be available before that. Otherwise, we're going to run into read after write or write after write issue. And also, I did mention that because we are following this convention for both read and writes, so since writes to the register files are edge triggered as well, this design that you see here can actually do a read and write at the same register with the same clock cycle. Okay, So actually we read, our read will get the value that was written in an earlier clock cycle. Okay, so one clock we write, and then right after that we can read, both on the triggered convention. Okay, and data value lines are also, of course, 64 bits. So I was having a question in Moodle. Somebody was asking me about that 5. So the reason we have 5, I mentioned, because we have 32 registers, but the width of the register are 64 bits. So don't confuse these two. So that was for the R format instruction. Let's have a look at the difference between your R type instructions and your memory instructions, and then we're going to see the load and store one after this. Okay, so in essence, in RISC-V, your R type instructions and memory instructions for the data path that we need to allow both of them are pretty similar, except there is a small difference that I'll describe it in the next slide. So you're going to see the text of the difference, and then we're going to see the design as well. So the arithmetic logic instructions use the ALU, right, with the input coming from 2 registers, because we need to compute something between the 2 registers. So we need 2 registers as input. The memory instructions, right, can also use the ALU to do the address calculation. Although the difference here is the second input that is going to use for memory instructions will only be used as a sign index 12-bit offset field from the instruction. So I'll show you the instruction later, and you see what are the difference in addressing that. And the value is stored into a destination register comes from the ALU, right? Or on the case of the memory, it's going to come, or the memory for the case of the load. So if you want to load something, it's going to come from memory. Okay. In general, as you know already, the memory instructions can also use ALU, so they are pretty similar. So what we have here in the design, okay. So for both of them, the only difference here is the way we play around with the func 8 and the RD here. If you take a look at your green sheet, so both of them are in R. The other is in SP. Okay. So for the R, we have 7 bits here for func 7. We're going to use the IAM 5 to 11 on the first 7 bits and 0 to 5 on that fourth one, or fifth one actually. So the first 5 bits are going to be here, and then after that, the next 7 bits are going to be there for the load and store, right? Okay. But on the case of the memory instructions, if you take a look at your green sheet again, so the SP type, we have 12 and 5 to 10. So for our 7 bits here. For those first 5 bits on the other side, we have 1 to 4 and also the 11. So that's the only difference between these two. Other than that, the rest are looking pretty similar. Okay. Questions? All right, so now we have designed all those 3 different smaller design, so for branch, for load, and for memory, right? So if you put all of them together, that's going to be our full data path, okay? So again, the branch instruction uses the main ALU, right, to compute 2 registers. Let's see here. So as you see, this data path that we just designed by adding those three different smaller modules together can execute basic instructions. So what it can do is actually a load store register, right? Using the register files, the ALU operation, and also branch. Okay. It is able to do all of those in one cycle. So each of those can be done in one cycle. So branch in one cycle, store in one cycle, so on and so forth. If you want to integrate the target address branch, if you were to go to a target address, actually we need another additional multiplexer to send us to the target one. But the current design, as you see, it's going to come back here, the PC, or just if we decided to go somewhere else, we need another multiplexer. But this is a very basic, let's say, processor that only able to do load and store, memory, and branch. Okay. Program counter. So when you start for each of the lines, it's going to add it +4, or if it has to be branched, it's going to branch to a destination address again. If not, it's going to come back and add +4, and then it's going to go for the rest of the program. All right. Again, if you ever miss any of those details, either you can refer to the lecture videos, or also the book is the best reference. So all the details are in the book. But make sure to start reading the book. It's going to be helpful in general, right? Okay, so that was our full data path. Let's talk about a little bit about the ALU control. How we're going to decide what to do with ALU, right? Here. So in order to control that ALU module here, right, for doing certain functions like AND or add subtract that we are interested in, doing with this data path we just designed, okay? So depending on the instruction class, the ALU will need to perform one of these 4 functions, right? For load and store, we use the ALU to compute the memory address by addition. So this will send the job for us for load and store as well. For the R-type instructions, right, the ALU needs to perform one of the 4 actions actually. So AND or add or subtract, right? We might use either of those. And we're going to choose that depending on the 7-bit func7 field, right? Let me see if so just like this, yeah, we're going to decide what to do for load and store, okay, using these bits. And also, in certain cases, we might need the 3-bit func3 as well, right? All right. Also, for the conditional branches, if those instructions were that were to compare were equal, right? The ALU subtract 2 operands and test to see if the result is 0. So this can be used also for conditional branches as well. So with this, we can mostly do all of the stuff that we need to do for the data path. Okay. So there is one more thing is needed to discuss, and that is how we're going to control that itself. So we can generate the 4-bit ALU control unit, right? The input for that unit using a small control unit that has an input of func7 and func3, so that's 7 and 3 bits, and also another 2-bit which we call here as ALU up. So you can see it in the second column. Okay. So these 2 bits can control up to 4 different ALU processes. But let's see how we're going to use it here. So ALU up indicates whether the operations can be performed. I mean, should the operation was load and store, subtract, or I don't know, if it was a branch. So we're going to do the test if 0, right? And that's why we need to know the func7 and func3 for that here. There are some operations here that I highlighted in the opcode field as cross, which we call it don't care. And these don't care operations are for the ones corresponding to either 0, 0 or 0, 1 in ALU up. So when the value is 1, 0, we actually need to use these values. Otherwise, we don't care about the opcode field on the case of load, store, and branch equal. Let's see what else I can talk about here. Does anyone know why we have don't care here? I mean, any hints, ideas? What is it? Yeah, close enough. Because in general, the desired ALU action does not depend on that 7-bit func7 or func3, right? So we don't need to actually look at the opcode field, so that's why we don't care about it. So we call it a don't care opcode here. Okay. So these were the different type of instructions we had, right? R type, I type, SP type. So now we have to set up the ALU control input based on the 2-bit ALU up control, right? Yeah. So in general, we use multiple levels of control because it eventually can reduce the size of the main control unit. See, we have different level of control. Because in general, if we use several small memory control unit, it's going to reduce the latency. Whereas we had one giant memory, one giant ALU control that does everything by itself, it would potentially increase the latency and the processor would just work slower and slower, right? So that's why we use several small control units to just keep the latency as low as possible. Also, we call this table a truth table, right? And as you see, many of the bits for many of the ALU up are similar, right? When the output is certain ALU, right? Addition and subtraction and branch. Okay, so let's see what we have here. So it actually shows that how the 4-bit ALU control is set depending on these input fields, right? In practice, this truth table could be very, very large, but just as an example, we have a subset of this here, right? For many of the instances, we still, the same goes with the truth table. We don't care. So those crosses are the don't care state because they were not actually needed under the specific line. Okay. The inputs that we have in the truth table are ALU up and func field, right? So the func field and ALU are the input. And so here we are seeing a subset of that. For example, the ALU up does not use the encoding 11. You see, we have either 1x or 00 or x1. So instead we have, right, is this or 01? We don't have 1 here. Thus, we only need these 4 func field bits as input for ALU control instead of 1, 0. Okay, does that make sense? Because for some of them, some of the lines were not necessary, right? All right, putting them all together, you're going to have a control unit such as that. Let's see. That does control using the instructions that coming here from 0 to 6. So there are 0 to 6 bits here that controls branch, memory read, mem to register, ALU up, mem write, ALU source, and register write. Okay, that will feed to the ALU control for the ALU. One of the output of the ALU will be output to where we do the branch, right? That's the comparison for the branch. And one way is going to come back to the PC. And if the branch was taking, we needed another multiplexer to just go to the target branch. All right. Any questions? You seem very energetic and active today. All right. No more questions? So with this Datapath with control, we can just do the control for our 3 different instructions that we talked about before. So the R type instruction, right? You see the different colors. So those that are activated and those that are not. So the R type, we don't need this because it's for the branch, right? For the load instructions, the difference is you need memory, right? One of the registers, and the write because you're reading from this and you want to write to that. So you need the write modules, write data, and write register, right? That's the difference here between load and R type. Okay, and for branch, because you don't load anything, so you don't need the write register from the register file. So these are great, you see, and only this side that decides to increment the PC counter by 4 or just branch to the target address is going to be needed. Okay, so that's the difference in these 3 situations. for your data type. All right. So gradually, we try to improve this pipeline, this data path that we built by different optimization techniques like pipelining and other techniques that you gradually learn mostly after midterm, by also doing your labs as well.
So does BEQ and BEQ have the same pipeline as BEQ?
Not necessarily, no. But here we only have BEQ. Yeah. It's a simplified sort of processor. It would make it bigger and bigger, right? This doesn't do that now, for now. It's a very small scale processor. All right. I guess you're very tired. So, and midterms are, yeah, are on the way. So, we don't see each other, thankfully, next week. And then in 2 weeks, yeah, I'll see you on Monday, perhaps. Yeah. In 2 weeks, Monday. All right.